Okay, so with the SI system of measurement, there are certain types of units that are sort of the official unit for certain types of measurement. So if you're looking at length, the official unit would be the meter. A meter is just a little bit longer than a yard, and its symbol is M, lowercase m. For mass, the official metric unit would be kilogram, and the symbol is just kg. It's hard to convey it, but that's a lowercase k. Time has, oh, a kilogram is about 2.2 pounds, by the way. Time has the official unit of seconds, for which the abbreviation is just a lowercase s. Seconds in the metric system is actually the same as seconds in the English system. They haven't managed to decimalize time yet. For temperature, the official metric unit in the SI system is not what you probably think it is. If you know anything about the metric system, you probably would say Celsius or centigrade for temperature. And that's right outside of chemistry and physics. But in chemistry and physics, we use a unit called the Kelvin. And that's a lowercase k. Or sorry, not a lowercase k, capital K for the Kelvin. We use kelvins, we'll get into this more detail later, but the reason we use kelvins is that they represent an absolute temperature scale. Most measurement systems are absolute by nature. So for length, it doesn't really matter whether you're talking about English units or metric units. 0 means nothing. So a length of 0 inches means nothing. A length of 0 feet means nothing. A length of 0 meters means nothing, and so on and so on and so on. But temperature is not like that. A measurement of 0 degrees Celsius does not mean no thermal energy at all. In fact, there's still quite a bit of thermal energy at 0 degrees Celsius. Even 0 degrees Fahrenheit, which is quite a bit colder, does not, mean zero thermal energy at all. And so that's why we had to have an absolute temperature scale where 0 is really nothing at all in terms of thermal energy. In fact, 0 Kelvin is known as absolute 0. It's the lowest temperature that can ever be achieved, even in theory. So that's why we need to use a different unit for science or chemistry and physics. There are other units that are not really important in this class, so we're not really going to cover those. We'll just leave that there. And this brings us to the math packet. The math packet is posted on Blackboard. It's something that I normally print out and give to students, although I usually post it on Blackboard also, in case they lose it, which many of them do. And it will be basically the math packet will be our textbook for the first couple of weeks of the course. The math packet is actually entitled Math Section Handouts, in case it's listed as that under that in Blackboard. So you can actually, you can look at it online or you can print it out, whichever you prefer. Okay, the conversions that are gone over in the math packet start out with some approximations. The first page after, by the way, in the introduction to the math packet, it says, let's see. These handouts will be used during the first several weeks of class. That's true. Most of these will be gone over in class, but some may just be used for additional practice on your part. That's true. The part where it says there is no homework in this class, that's actually not true. This was written up by a former instructor, and I've changed the policy. There is homework now. So, but the homework will not be from any of the handouts in this math packet, so you won't have to hand anything in the math packet in. And be sure to keep it handy, because like I said, this is what we're doing for the first couple weeks in the class. Also, there can be some useful information found in Appendix A and Chapter 1 of the textbook, but basically what we do is going to be from the math handouts for the math packet. Okay, so yeah, so getting back into the content, the first page after that one is approximate comparisons. And this can be used for, this can be useful for some purposes. I'm not going to go into as much detail as the math packet does on working through the math of approximate conversions, but just to sort of get the idea of what these metric units are like, we can look at some of the approximations. And so we need to look at some approximations involving metric units. That's what this is up at the beginning. So we'll have some English systems and some SI units. The inch is a well-known measurement in the English system. It was officially supposed to be the distance from the end of your thumb to your first knuckle. Okay. Approximately 2.5 centimeters, which technically, I guess, is not an SI unit. So let's call this side metric rather than SI. So 2.5 centimeters. So about 2.5 centimeters, that's an inch. You can also remember that, well, the inch is the distance from the end of your thumb to the first knuckle. A centimeter is probably about the width of the tip of your little finger. And so obviously a centimeter is smaller than an inch. And so there should be more centimeters than there are inches in any given measurement. And that's true. One foot, which supposedly the length of an average foot, I think that the people that they measured for that had awfully big feet. Maybe it was a Sasquatch convention or something. But anyway, that's what it was supposed to be. Maybe it was Charlemagne's foot or something. He was supposedly 8 feet tall. But anyway, 1 foot in terms of metric units would be about 1/3 of a meter. To be a little less approximate, it would be more like 0.3 of a meter, 3/10 of a meter. One yard, which is also 3 feet, of course, is about, or sorry, not 1.1. It's about 1 meter. If you're approximating, 1 meter is close enough for a yard. A yard is actually a little bit less than a meter. 1 mile is about 1.6 kilometers. 1 pound would be approximately 1/2 kilogram. So like I said, 1 kilogram is 2.2 pounds approximately. One gallon is 4 quarts, and as it turns out, a quart is just about a liter. So 1 gallon is also approximately 4 liters. Okay. 1 fluid ounce is about 30 milliliters. So that should help you with. Okay, so now that we've looked at English to metric approximations, we can look at the other way around. Metric to English. And if you look at the metric unit of 1 meter, well, that would be approximately, oops, let me straighten it up, approximately 1 yard or 3 feet. And a centimeter, which I said is also, about the width of the tip of your little finger, would be about 0.4 inches. 1 kilometer would be about 0.6 of a mile. And 1 kilogram ballpark figure would be about 2 pounds. 2.2 is, more accurate, but even that's not perfectly accurate. 1 liter would be 1/4 of a gallon, or about a quart. Okay, so a liter is about a quart. 5 milliliters is equivalent to 0.17 ounce, which is 1 teaspoon. See, who knew a teaspoon was 0.17 ounce? This is the English system for you. Weird, weird stuff sometimes. And I'm not doing any of the calculations with approximations that we have here, between the tables and after the second table, because we have plenty to do with more exact calculations. But there is a section in a couple of pages that says realistic or ridiculous, and we can do that. Because, again, having a ballpark, at least approximate understanding of the magnitudes of these units can be very useful when doing things like unit conversions, because it makes it possible for you to tell whether your answer is plausible or ridiculous. So under the heading realistic or ridiculous, we need to determine whether each of the following statements is realistic or ridiculous. Number 1 is the height of a life-size statue dedicated to a former president is 5 meters. Well, when you think about it, 5 meters is about 5 yards, which would be 5 times 3 feet, because each yard is 3 feet. And that would be 15 feet. While 15 feet is a perfectly reasonable size for a statue, the question does say that it's a life-size statue. Now, even Abraham Lincoln wasn't that tall. So, I mean, that he wasn't even half that tall. So that is ridiculous. Okay, definitely not life-size. The mass of a serving of peas is 1 kilogram. One kilogram is about 2 pounds, remember. 2.2 to be a little more exact, but about 2 pounds. That is a lot of peas. And for 1 serving, absolutely not. ridiculous. For 3, a pencil, assuming it's a new pencil, is about 20 centimeters long. And if we want to say 20 centimeters in inches, well, we said each centimeter is about 0.4 of an inch. So 0.4 times 20 would be 8 inches. And this is kind of a preview of the way that we'll be doing unit conversions. We take the quantity that we're given and we multiply by some conversion factor. We were told in the last table that there's 0.4 inch for every 1 centimeter. And the units that you're starting out with, you want to go on the bottom of this conversion factor, and the new units you want to go on top. So when you take 20 centimeters times 0.4 inches over 1 centimeter, you'll notice that you're effectively dividing centimeters by centimeters, and those units cancel, leaving you with inches. Then all you have to do is multiply the numbers. 20 times 0.4 is 8. And 8 inches is a reasonable length for a new pencil. Oh, sorry, that was 3. 4. Particular textbook is about 2.5 centimeters thick. .5 centimeters, as the table says, is about 1 inch. And that is reasonable. About 1 inch, that's a reasonable size thickness for a textbook. It says a Thanksgiving Day turkey has a mass of about 20 kilograms. Okay, 20 kilograms. And it says that each kilogram is about 2 pounds. So if we multiply 20 kilograms times the fact that there are 2 pounds per kilogram, again, kilograms end up canceling out. 20 times 2 is 40. 40 pounds. Now, that's a really big bird. I don't know if you could find one that big anywhere, but that's pretty ridiculous. Okay, so that's ridiculous. Okay, 6 is the length of the C building hallway is about 100 meters. Well, we already said that a meter is about a yard, so 100 meters is about 100 yards. And 100 yards is 300 feet. I don't think it's that long, but that's not ridiculous. So we'll say reasonable. And since this is an online class this summer, a lot of you guys have probably never actually seen the C building. So 100 yards is certainly reasonable for the length of a hallway in an academic building, though. Okay, so number 7, different distance from Sanborn to Rochester is 500 kilometers. The table says that there's about 0.6 miles for each kilometer. So 500 kilometers, 500 times 0.6, that would be 300 miles. Not reasonable, ridiculous. Because in fact, it's around 60 miles. Maybe a little more than that. A newborn baby has a mass of 3.5 kilograms. Okay, so 3.5, and there's about 2 kilograms per pound, 2 pounds per kilogram. Kilograms cancel. 3.5 times 2. And that is reasonable. Sorry. Number 9 says it took 80 liters of gasoline to fill the gas tank of a truck. Well, we would take 80 liters and use the fact that a liter is about a quart, and there are about 4 liters per gallon. And that means 20 gallons. There are lots of cars that have 20-gallon tanks, and that's certainly reasonable for a truck. It's pretty big, but not ridiculously big. Okay. And it says here that you should pack at least 2 liters of water for a hike lasting a few hours. Well, what volume would that be in gallons? Well, let's see. There's 1 gallon for every 4 liters because a liter is about a quart. Liters cancel. 2 divided by 4 is 0.5 gallons. In other words, half a gallon. That's reasonable. Okay, so that hopefully will help you sort of estimate relative sizes. The next page is more approximations. And like I said, I don't really want to get you too accustomed to using approximations for measurements or for unit conversions. So I'm going to skip over these approximations and go on to the next page, which is on measurements. So measurements. We actually mentioned measurements back a few minutes ago, so you can refer to that discussion. A measurement is really determination of the magnitude of some physical property of some object or substance by comparing it to some agreed upon reference point. So like when you measure the length of something with a ruler, you're comparing the length of that object to the number of agreed upon units, like say inches or centimeters, that are equivalent to that object. And so that's essentially what you're doing in a measurement. Remember that in practical terms, a measurement consists of a number and a unit. And both of those parts are equally important. A number without a unit is meaningless, and a unit without a number doesn't mean very much either. Okay? The unit tells you the unit gives the type of measurement. And usually it tells you something about the magnitude of the object also. So if you have a measurement that's in inches, then you can tell, first of all, that it's a length or a distance. And if it's done in inches, you can also tell that the size of the object is probably fairly small, because you're not going to be measuring really big objects in inches. It wouldn't make sense. You'd end up with a huge number. If you wanted to measure, the length of the lot that your house sits on, you're going to probably do that in feet or yards, but not inches. If you measure the distance from here to Rochester, you're going to do that in miles, not in inches. You could do it in inches, but you would get a ridiculously big number to go with the unit. So we usually choose a unit that is close to the size of the object or the property that's being measured, so that we end up with a reasonable number. Okay, because generally people don't like, even scientists don't like dealing with numbers that are really huge or really tiny if we can avoid it. So we'll usually choose a unit that's close in size to whatever property is being measured, and you get a reasonable number out of it. Measurement also often involves estimation. We think of measurement as being something that we do exactly, but often that's not possible to get an exact measurement on something. It really depends on what units your measuring device is marked off in, and what are the size of those units, and where does the object fall relative to an even number of those units. And so measurement often involves a certain amount of estimation. Okay. Because for the greatest accuracy, what you normally want to do Okay, so what you normally want to do is measure an object to the smallest unit that's marked off on the measuring device. And estimate one digit beyond that. And that is much more accurate than just leaving it at the digits that are certain when you're making a measurement. It's understood in any given measurement in science anyway. It's assumed actually that the last digit is a little bit uncertain. And we assume that the last digit of any given measurement is uncertain to the extent of plus or minus 1. That allows for the possibility that two different people might read a number differently, for example. So we can look at an example. If you're measuring the length of some, say, metal rod, and you're doing it on a meter stick, and you have the meter stick marked off as in, say, centimeters, and each centimeter is marked off into 10 smaller spaces. Like that. And your metal rod goes to this point here. Okay, and you want to measure the length of that metal rod. It's a little slanted there, so let me square off the end a little bit. Okay, there we go. So here is the length of that metal rod. Obviously, it is not exactly on one of those lines. And that means that for greatest accuracy, we're going to want to estimate how far that rod comes between the line just below it and the line just above it. First of all, we can write out what we know about the measurement. We know that it's greater than 37, but less, or it's greater than 27, but less than 28. So we know it's going to be 27 point something. And we also know that these little marks, because there are 10 of them between the 2 centimeter marks, these little marks are tenths of a centimeter. And we can count off those marks until we find the one that the length of the rod is just beyond. So we know that it's greater than 27.1, it's greater than 27.2, 3, 4, 5, and 6. But it's less than 27.7. So we're going to call it 27.6 something. So the 27.6 right there, that is the smallest unit that's marked off on the measuring device. And now we have to estimate how far the rod comes between the 0.6 and the 0.7. It looks to me like it's maybe about a third of the way. So we could call that 27.63 centimeters. But remember, since that last digit was estimated, we assume that it is uncertain to the extent of plus or minus 1. That digit is the second digit past the decimal point, so this measurement would actually be equivalent to 27.63 plus or minus 0.01. This allows the last digit to vary by 1 up or down. And that sort of basically allows for the fact that different people might read that differently. You might look at that and say, it looks like it's more like 2/10 of the way between the two tenths lines. And I'd say that's okay because we know that it's uncertain by plus or minus 0.01. So what this means is that that length is somewhere between 27.62 and 27.64 centimeters. That's what that really means. So it really creates kind of a range of possible lengths for that rod. And that is actually the most accurate way to measure the length of the rod, because obviously if we just said 27.6, that's definitely not right, because it's clearly more than 27.6. So we're going to try to estimate how much more. But we can really only estimate with any accuracy to just one place beyond the markings on the ruler. And so that's the way that you do measurements in general. Okay, I see that we're kind of out of time for this particular video. So I'm going to stop this part here and we'll continue on with the next part.